Hello and welcome to another one of our online lecture videos for differential equations. Today we're going to be taking a look at forced oscillations and resonance. Now we've already taken a look at similar systems from before. We took a look at m times x double prime plus c times x prime plus k times x equals 0, m referring to a mass, c referring to a dash pot for some dash pot constant, and k referring to a spring with a spring constant k. And when we had this set equal to 0, we are talking about there being no sort of environmental force, no external force, just talking about free motion. So this talks about the one-dimensional motion of a mass m that is attached to a spring with constant k, a dash pot with constant c with no external force. Now we're going to take a look at modifying this because now we have the tools and the machinery to modify it, so to speak. We're going to look at the differential equation. Left-hand side is still the same, mx double prime plus cx prime plus kx, but now equals a function of t. So no longer is it going to be a homogeneous second-order differential equation. Now we're looking at a non-homogeneous case. And this describes the one-dimensional motion of a mass m attached to a spring with spring constant k and a dash pot with dash pot constant c that is also acted on by some external force. And we say that machines with rotating components commonly involve mass spring systems, or something equivalent to this, in which the external force is something that's simple harmonic. So we think about some machinery hooked up, and maybe the machinery has some sort of wheel that turns with a sort of a pulley system, which is creating this simple harmonic motion through an external force. So now we're not just talking about the free system, now we're talking about a system that also has this added machine component to it and how that affects what's happening. And so we'd say, well, if that force then, if the external force is simple harmonic, that means it must be either some cosine or sine function. So f at t is either f sub 0 times cosine of omega t, or it could be f sub 0 times sine of omega t. Some sinusoidal function, where the constant f sub 0 is the amplitude of the periodic force, and omega is the circular frequency. So we get sort of this idea of this machinery with maybe some gear attached to it that's sort of working in this simple harmonic motion as well. Now, there's going to be a lot of ideas presented in this section, so I am going to break this up and do a couple of different videos. We're going to take a look at our lecture material, but there's also going to be a very important behind-the-scenes episode for this particular section where we go into greater detail about transient solutions, steady periodic solutions I want to talk about. I want to make some claims that maybe we noticed in the previous sections about how we expect those homogeneous solutions to decay over time. And I also want to talk a little bit more about some extra topics like resonance disaster and some other interesting conversations. So definitely check out the behind the scenes video. But just to try to keep this video a bit shorter, or at least an attempt to do that, I would like to save some of that material for a separate video. So definitely check that out. But let's go ahead and take a look at this first example. So we want to express the solution of the given initial value problem as the sum of two oscillations. And we're going to start by taking a look at problems that do not have a dash pot involved. So you'll notice that the x prime term is missing, but here we just have x double prime plus 9x equals 10 times cosine at 2t. We have an initial position is 0 and an initial velocity is 0 as well. Now the very first thing that we have to do, if we remember solving these with the method of undetermined coefficients, is to first take a look at the complementary solution by looking at x double prime plus 9x equals 0. So we first solved the homogeneous variant on this. And using the characteristic equation, we get r squared plus 9 equals 0, or that r squared equals negative 9, or then that r is equal to plus or minus 3i. So this carries with it a complementary solution, x sub c is some constant c sub 1 times cosine of 3t, plus some constant c sub 2 times sine of 3t. Now what's important here, and there's going to be a longer discussion about this in that separate video like I mentioned, it's important that my complementary solution And what I'm looking at for the non-homogeneous side of my differential equation, that these are linearly independent. And I want to really point out here that for my complementary solution, or the solution to the homogeneous, I have a frequency of 3, cosine of 3t and sine of 3t. When I take a look at this external force that's acting, it's not the same frequency, and that's important. This is 10 cosine of 2t. And it's important for a couple of reasons. But first of all, it means that I can go ahead and presume with a very natural guess for that method of undetermined coefficients. But it's also important that the natural resonance of my system doesn't contribute to the forcing function that we have. If that happens, then we get this phenomena that could happen known as resonance disaster, which we're going to talk about that a lot more in a separate video. But that's something that's important for a couple of reasons, not just for ease of solving, but also to make sure that we don't have something disastrous happening that we observe. But with that in mind, we'll take a look at a particular solution, and we guess this first. We say, well, since my right-hand side is 10 cosine of 2t, I'm going to make my guess some constant a times cosine of 2t plus some constant b times sine of 2t. Now, there's actually something that we could comment about this, and I'm going to show this in generating my solution with the method of undetermined coefficients. But since this left-hand side skips over x prime, I don't really need the sine term. We're going to actually see that even if I include it, that with this method of undetermined coefficients, it gets excluded at the end. But that's only because the first order derivative is missing in this case. But if we don't notice that, or if we're not thinking that far ahead in terms of calculus, it shouldn't make a difference. Because when I go and differentiate here, derivative of cosine is negative sine, and then chain rule with our inner derivative, we get negative 2a sine of 2t. And then derivative of b sine of 2t, again chain rule, gives us plus 2b cosine of 2t. And when I differentiate again, my second order derivative is going to give me now negative 4a cosine of 2t. And then here I'm going to get negative 4b times sine of 2t. And when plugging into the differential equation's left-hand side, I only need x double prime and x. So x double prime plus 9x is really what I'm focusing on. So here I can go and say, well, x double prime plus 9x is going to be equal to, let me write underneath here, x double prime is negative 4a cosine of 2t minus 4b sine of 2t plus 9 times x. Imagine distributing a 9 through x up there. That's a 9a cosine 2t plus, and then we're going to get a 9b sine of 2t. And then I can combine my like terms. So for example, 9a cosine 2t minus 4a cosine 2t gives me 5a cosine 2t. And similarly, 9b sine of 2t minus 4b sine of 2t gives me positive 5b sine of 2t. And that this should be equal to the right-hand side of my differential equation, which is this 10 cosine of 2t. So this should be equal to 10 cosine of 2t. But we notice from this right away that sine is missing, and we only have cosine on this right-hand side. So that means 5a, my coefficient on cosine of 2t, must be equal to 10. But is also meaning that this 5b, the coefficient on sine of 2t, has to generate 0, so that it ends up not sticking around. So then if I solve these, if 5 times a is 10, well, that means a is 2. And if 5 times b is 0, well, that means that b has to be identically 0. So sort of as I promised, that sine term doesn't end up needing to be part of this particular solution. So x sub p, that's a cosine 2t, so 2 cosine 2t, and then plus b, which is 0, sine of 2t, just gives us the particular solution, 2 cosine 2t. So in fact, our original guess would have been safe if we didn't include sine, but I think that's dangerous because if we're trying to establish a good workflow, when you see the mention of one trig function on that right-hand side, provided there's no issues with linear dependence, we want to actually select both of these. The only reason why sine really doesn't need to be included in this particular problem is because I'm skipping over the first derivative. Since I'm just going from x to x double prime, that means differentiating cosine twice over returns back to cosine. So then, that's, I think, a little bit much forward thinking. Maybe it's something that I think about a lot, but maybe isn't common to think about overall. So I'd say this is probably the best way to do the problem. And the differential equation is always on our side, letting us know the information along the way. And here it says, hey, you didn't really need the sine function after all for the particular solution, so let me get rid of that for you. And I think that's a safer way to go about it than to try to stare at the function and the differential equation for too long and try to make some ad hoc decision that might backfire if we're not careful. But so now that I have all of this, I can build my overall solution. And here we want to use that superposition principle where x is equal to the complementary solution plus the particular solution. So x, my function of t, is equal to a complementary solution. The solution to the homogeneous was c sub 1 cosine 3t plus c sub 2 sine of 3t. And we add to this our particular solution, the solution to the non-homogeneous, which is 2 cosine 2t. And now I have these initial values that I can work with. Right? Once we build this full solution, this entire description of our solution, we can now work with the initial values. X at 0 is 0 and x prime at 0 is 0. If I differentiate this, x prime at t, derivative cosine is negative sine, so with chain rule, negative 3 c sub 1 sine 3t. Derivative sine is cosine, so with chain rule, 3 c sub 2 cosine 3t. And then here I'm going to get a negative 2 times 2 gives me negative 4 sine 2t. And now I can plug into x and x prime. So if I go through this, switching between colors, x at 0, and remember, cosine at 0 is 1, sine at 0 is 0. So if I remember that, I'm going to get c sub 1 times cosine at 0, which is c sub 1 times 1, which is c sub 1, plus c sub 2 times sine at 0, which is c sub 2 times 0, plus 2 times cosine at 0, which is 2 times 1, which is 2, and that this should be equal to 0. But now this would solve right away. C sub 2 times 0 is 0, so that term's gone. So c sub 1 plus 2 is equal to 0. Means that c sub 1 is equal to negative 2. And plugging into x prime, so x prime at 0, well, negative 3 c sub 1 times sine at 0 is 0, plus 3 c sub 2 times cosine at 0 is 1, so that's 3 c sub 2 times 1, or 3 c sub 2, minus 4 times sine at 0 is going to give me 4 times 0, which is 0. And we said x prime at 0 has to be equal to 0. So what is this saying? Well, this is saying that 3 times c sub 2 must be equal to 0, which is only true if c sub 2 is 0. So now that I know the values for c sub 1 and c sub 2, I can include those back in my overall solution to write out how that solution looks as a particular solution, including both parts, homogeneous and non-homogeneous. So this is what x at t was looking like before, just returning back up here. We know c sub 1 is negative 2, so that's a negative 2 cosine 3t. Since c sub 2 is 0, this second term is actually gone now. 0 times sine of 3t is just 0, so see you later. And then I'm left with this other term, 2 cosine 2t. So plus 2 cosine 2t. And this would be my final solution. Now, I did get a bit lucky here. If I go back to the initial instructions, this said to write the answer as the sum of two oscillations. And we would do that in the same way that we did previously when we took a look at the sort of free systems where there wasn't an external force involving that coefficient capital C and trying to find cosine of omega t minus alpha. But I was lucky in the sense that in my particular solution, the sine term dropped out, so I just was left with cosine. And in my complementary solution, when I solved for constants C1 and C2 after putting everything together, I did see that C2 was 0, which meant that my sine function in the complementary solution didn't want to stick around either. So this is actually already in the form of the sum of two oscillations. If I had those sine terms left over, well, then I'd have to go through all those extra steps that we saw before. So this is actually all set for us to go as part of our answer. And I can just comment briefly that if these were the same frequency, if it wasn't cosine 3t and cosine 2t, if they were both, for example, cosine 3t, that could lead to that so-called resonance disaster, which is something that we'll take a look at in the behind-the-scenes video. So stay tuned for that. Definitely want to talk about that. But let's take a look at another example. So again, express the solution as the given initial value problem as the sum of two oscillations. We have x double prime plus 100x equals 225 cosine 5t plus 300 sine 5t. We have initial position, x at 0 is 375, and then initial velocity is 0. X prime at 0 is 0. Same idea. To start, I need the complementary solution, which means looking at the homogeneous variant on the differential equation. So x double prime plus 100x equals 0. Get the characteristic equation going. R squared plus 100 equals 0. So r squared is equal to negative 100. So r is plus or minus the square root of negative 100. So this gives me r is plus or minus 10i. And we remember from the characteristic equation, since this is pure imaginary, how the solution is going to look, that my complementary solution on x is going to be some c sub 1 cosine of 10t plus some c sub 2 times sine of 10t. But it's very important to notice that the frequency of the complementary solution is not identical to the frequency of the forcing function. That would be a huge potential hazard. So that's good. That means the natural oscillation of my system is not going to mimic what's happening with the forcing function, which could create all sorts of those resonance disasters. We'll talk about those in that separate video. I love sort of like keeping you hyped about it, because I really think it's going to be a fun topic to discuss. But I'm just sort of pointing out some ideas. Try to think of some examples of resonance disaster if you've heard of it before as we're going through the lecture. And then, let me know on the discussion board if you've ever observed it firsthand or if you've heard stories about it. Fun to talk about. But okay, so since these are different arguments on cosine and sine, I got 10t and 10t, I got 5t and 5t, they're not the same. That means I can wager my guess, as I would most organically, saying that my guess for the particular solution, and here since cosine and sine are both present, I shouldn't think about excluding either of them. I would just say some general constant a times cosine of 5t plus some general constant b times sine of 5t, and then going through to find the second order derivative. So first order derivative first gives me negative 5a sine 5t through chain rule, and then plus 5b cosine 5t. We do chain rule one more time to find the second derivative. This is going to give me a negative 25a cosine 5t. And then here I'm going to get a negative 25b sine 5t. Just a bit of chain rule. Differentiate a lot of cosines and sines in the course, that's for sure. Now I want to look at my differential equation, which is x double prime plus 100x. This is going to be equal to x double prime is right there. That's negative 25a cosine of 5t minus 5b sine of 5t plus 100 times x. So imagine multiplying 100 through. It's going to give me 100a cosine 5t 100a cosine 5t plus 100b sine of 5t. Now let's combine the like terms. So on cosine of 5t, I have 100a minus 25a, so that's 75a cosine 5t. And on sine of 5t, same idea, similar, right? 100b minus, I lost my 2, 25b, 25b. 100b minus 25b is going to give me positive 75b sine of 5t. Sorry for that typo there. And this should be equal to the right-hand side of my differential equation, this 225 cosine 5t plus 300 sine of 5t. So 225, if I got room for it, 225 cosine 5t plus 300 sine of 5t. And I can set those like coefficients equal. So on cosine, I have 75a and 225 comparing left and right. So that means 75a must be equal to 225. On sine of 5t, I have 75b should be equal to 300. And looking at all these numbers really makes me think of, laundry day dealing with quarters. So let me know if you're doing laundry day with your quarters, then we probably have a good idea as to what this looks when we divide. 225 divided by 75 is going to give me 3. 300 divided by 75 is going to give me 4. Arithmetic with quarters. I like to do that. So then now I know what A and B are, so I can go back to my particular solution, which we said was A cosine 5t plus B sine 5t. I can pop those values in now. Method of undetermined coefficients was successful. Now I know, now I see it all, right? A cosine 5t is 3 cosine 5t. B sine of 5t is going to be 4 sine of 5t. Now, though, so wait, there's more, quite a bit more. I can build my overall solution. X is equal to the complementary plus the particular solution. Let me do this underneath here. So x at t, what was my complementary solution? We found that earlier. C1 cosine 10t plus C2 sine 10t. So C1 cosine 10t plus C2 sine of 10t plus my particular solution is just fresh out of the oven, 3 cosine 5t plus 4 sine 5t. And I'm also going to want the derivative to work with the initial values. Let me find the derivative right now. I'm already here with the function. I'm going to find its derivative at some point. Let me do that now. Can't stop, won't stop. Make that a hashtag. Can't stop, won't stop. So here I get chain rule, a lot of it. Minus 10 c sub 1 sine of 10t plus 10 c sub 2 cosine of 10t. Careful with chain rule here. Minus 5 times 3 is going to give me 15 sine of 5t. And then plus, here I'm going to get 5 times 4, chain rule, 20 cosine 5t. What are my initial values? They didn't look fun, but they're maybe not the initial values that we had expected, but they're the initial values that we got. X at 0 is 375. And my favorite, x prime at 0 is 0. Let's see if we can rock and roll with these. So let's go to x. Let me switch my colors. Let me know if you're still digging the color coding. I like it. X at 0, remember, 10 times 0 is 0, 5 times 0 is 0, cosine at 0 is 1, sine at 0 is 0. So it shouldn't hopefully take too much work to see that if I plug 0 in, I get c sub 1 times 1, which is c sub 1. Sine at 0 is 0, so see you later. Cosine at 0 is 1, so 3 times 1 is 3. Sine at 0 is 0, so this term is 0 as well. So not a lot of these things stick around. I get x at 0 is c sub 1 plus 3, but x at 0 should be equal to 375. So it looks like c sub 1, if I subtract 3 over, is 372. And then if I want to work with x prime, let me do that over here. X prime at 0 is 0. Well, what is x prime at 0? Remember, plugging into cosine and sine shouldn't be too terrible. Sine at 0 is 0, so first term is gone, out of the running. Cosine at 0 is 1, so I get 10c sub 2 times 1, which is 10c sub 2. Third term, sine at 0 is 0. Get out of here, scram. Now then, 20 times cosine at 0 is 20 times 1, which is 20, and that this should be equal to 0. So all that's left is 10c sub 2 plus 20 equals 0. So then 10c sub 2 is equal to negative 20. If I want to divide by 10, sure I do. C sub 2 is negative 2. And now I see it all. So I can go, when I do this in pink last time, whatever color you like. Now I can write my solution in full. Now I know everything about it. I have that particular solution, I should say the specific solution, the sum of the particular and the complementary, but now I know all the pieces to it. So c sub 1 cosine 10t, but c sub 1 is 372. So 372 cosine of 10t plus c sub 2, but c sub 2 is negative 2 times sine at 10t plus 3 cosine 5t. Got to bring that blackboard down so I don't write over my forehead. And then plus 4 sine 5t. But here's where we get bonus round. Yes, because here I want to write this as the sum of 2 oscillations, and now I have 4 pieces. So what I want to do is I want to find the like cosines and sines with the same argument. So cosine 10t, sine 10t, these are going to get grouped together into one cosine function. And cosine 5t, sine 5t, these are going to get grouped together into one cosine function as well. And for each of these, I want to find capital C. So here, capital C is the square root of a squared plus b squared, so that's 372 squared, plus negative 2 squared. And this feels like a job for our calculator friend. Where'd he go? Taking a little robot break. Beep, boop, bleep, 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 bleep. Gotta plug into the calculator. Doop, doop, doop. You don't have to. I'm not saying that that's the only way to do it. I'm saying I knew 372 squared wasn't going to be fun. But I believe in you that if you square these and add them, negative 2 squared is fine, that's 4. You should get 138,388. And while we're at it, we'll find alpha is tangent inverse of b, let's call this alpha sub 1 and c sub 1, since I got another round of it, color coding as well. So remember, it's b divided by a, tangent inverse of b divided by a, which is negative 2 divided by 372. But wait, I have to think about what quadrant I'm in. If I were to plot a comma b as an ordered pair, a is positive, 372, all the way out there, but positive. B is negative, so that's going to put me in quadrant 4. If you remember, this means I have to add 2 pi to this value. So alpha, for the green stuff, is tangent inverse of negative 2 over 372, and then plus 2 pi. I'm responsible for that plus 2 pi. So that looks like a lot of fun. Over here, it looks a little bit more my style, a bit more mild. c sub 2 is square root of, again, a squared plus b squared, but we're looking over here at these two terms. So 3 squared plus 4 squared, which this is not a bad one at all. 9 plus 16 gives me 25. So c sub 2 is just 5. And alpha sub 2 is tangent inverse of b over a, which is 4 over 3. But if I think about the quadrant that this is in, a is positive, b is positive, so that puts me in quadrant 1 somewhere, which means I don't have to add anything. That tangent inverse of 4 over 3 is already going to give me something from the principal branch, which is already going to be between 0 and pi over 2. So I'm already set with this. So now what I can do is I can write these finally in their complete form. So x at t, it's going to be capital C for the first one, which is square root of 138,388 times cosine of, and what was it here? It was 10t, but it has to be cosine of 10t minus alpha. Now, if you don't have a calculator and you're not going to be allowed one on the exams, this is as far as you could go realistically to find alpha. But if you were to pop this into the calculator, it would give you 6.27781. So that's my capital C cosine omega t minus alpha for the green stuff. But then I want to add to this. I'm going to have to move down here because I do not have enough space. But then next, c sub 2 is 5 times cosine of, and I keep that argument the same, that's 5t minus alpha. And here alpha was just tangent inverse of 4/3, which again I need a calculator to help with that, but that gives me 0.927295. And this is going to be my sum of two oscillations right here. So this plus this. Whoops. I'm just trying to circle it because I'm proud of my work. So there we go, sum of two oscillations for this. I have this extra page here for notes. I'll say way more fun. Way more funner. Because before we just had, no external force. This is way more interesting with the external force acting, because we get a chance to then talk about the method of undetermined coefficients and to build over those cosine functions twice in some cases. I want to talk about practical resonance for a system. In order to do this the quickest way for multiple examples, we're going to build an expression, sort of a function of omega, capital C of omega, on the steady periodic function for mx double prime plus cx prime plus kx equals f sub 0 times cosine of omega t, with omega not equal to omega sub 0, x at 0 equals x sub 0, x prime at 0 is 0. Now, I'm going to talk a lot about this in that separate video, the behind the scenes, but there's some special terms that we can introduce in this section where we say the complementary solution can be referred to as the transient solution. And sort of a spoiler alert on that, this is because this part of the solution is going to, when we have a dash pot, so not in the previous examples, but in these current ones, since we have a dash pot now, this is going to die off as t increases, whereas the particular solution, we refer to this as the steady periodic solution, so x sub sp, so transient solution versus the steady periodic function. This part of the solution will live on as t increases, and this is going to dictate the behavior in the sort of the long haul of everything. But we'll talk much more about that in the behind the scenes video. It is a very important topic, so that's definitely not a video to skip. Don't try to think of it like extra. Think of it like bonus. Think of it like we want to watch it because there's more discussion to be had. But I don't want these videos to be 7 hours long. I would like that. I just feel this pressure that maybe not all of you would like that. But let me know on the discussion board if you want me to just ramble for 7 hours. And sounds like something I'd be good at. This first mention here that omega does not equal omega sub 0, what this is really saying is that my complementary solution is linearly independent from my particular solution. Or here we said the complementary solution can be thought of as the transient solution, dying off as t goes on, versus the particular solution as the steady periodic function, which is going to dictate the behavior eventually. And if we think about a machine component powering some mass spring system, well, there's probably going to be some startup involved where maybe the spring system is doing some oscillating on its own, but once everything gets, kicked into gear, everything's fired up, after a little bit, it's going to be that machine component that is generating the behavior. And that's sort of the idea. But so let's see if we can build this expression. And this is going to be definitely an involved process. So if you were waiting on that second cup of coffee for the day, now is the time. Because we are going to do this in general. Since I'm told that omega does not equal omega sub 0, that means the frequencies in my complementary solution and my particular solution, aka my frequencies in the transient solution and the steady periodic solution, do not compete with one another, so that I can just begin with the method of undetermined coefficients. And I'm expecting to be successful with that, is what we're saying. So then my particular solution, I'm just going to say that's some a cosine omega t plus b sine of omega t. And if I differentiate this, that's going to give me negative omega a sine of omega t, thinking of omega as just a constant and using chain rule, plus omega b cosine omega t. And if I differentiate again for the second order derivative, I'm going to generate another inner derivative, so negative omega squared a cosine omega t. And then here I'm going to get a minus sign and another omega through chain rule, so negative omega squared b sine of omega t. Now I want to build this left-hand side, which is m x double prime plus cx prime plus kx. And just imagine multiplying through. So if I multiply m into x double prime, I get negative m omega squared a cosine omega t minus m omega squared b sine of omega t plus now c times x prime. If I multiply c in here, I'm going to get negative c omega a sine omega t and then plus c omega b cosine omega t, and then plus k times x. So then multiplying k into x, that would be plus k times a times cosine omega t plus k times b times sine of omega t. But now I get to collect all my coefficient on cosine omega t and on sine omega t. So here's everything on cosine omega t plus everything on sine omega t. And let's look for the cosine stuff. So here, starting at the end, I guess, I have cosine omega t times Ka. So Ka is part of the coefficient. Think of grouping them together and factoring out. I'm going to have plus c omega b is attached to cosine. So c omega b. And then this first term, right? Minus m omega squared a. Do the same for sine omega t. So on sine omega t, I have kb. And then here I have negative c omega a. And then negative m omega squared b. So now I have everything grouped nicely. And this should be equal to f sub 0 cosine omega t. So this should be equal to f sub 0 cosine omega t. So what does that mean? Well, it means two things. It means my coefficient, and oh, it looks crazy. Oh, I didn't sign up for this. My cosine coefficient should be equal to f sub 0. So k a plus c omega b minus m omega squared. I can fix that. You guys are worth it. I'll use the eraser there. Minus m omega squared a should be equal to f sub 0. Coefficient on cosine should be f sub 0. And my coefficient on sine, what should that be? It shouldn't be there, so that should be a 0. So that also means then that k b minus c omega a minus m omega squared b should be equal to 0. I want to work with this. I want to get a substitution. I'm going to use the second equation because it's easier to get a substitution from to plug into the first equation. If I'm trying to do this, I think it's going to be fun no matter how you choose to do it. But A appears twice, B appears once. So if I can substitute for B, that would maybe be marginally better. So let me go here and try to isolate B. So I can add C omega A over. And of the remaining terms that have B, I can factor B out. And I'm left with K, since I had KB, so K. This has got moved over, and then minus M omega squared. And that's factoring, and then I moved this one over there, and I can solve for B now. Pause the video right now, go to the discussion board, and tell me if you think this is going to be a beautiful result or a not so beautiful result. So we got solving for B, just dividing C omega divided by K minus M omega squared, and all of that times A. This is my substitution. So then I can go to this equation here, and let me just go down here to some, I got more space. So we have K times A plus C omega times B. I'm going to plug in for B right there, minus M omega squared A is equal to F sub 0. And here's my substitution. That was C omega times B, but B is C omega. Even my computer doesn't like that I'm doing this task right now, but too bad. And then A. So just pop that substitution right in. It doesn't have to be so bad. We're in this together. We're in it to win it. So all of this is on A. A, first term, A, second term, A, third term. So let's factor A all the way out. It's equal to F sub 0. What do I have? I have K, and I have plus. I have C omega times C omega is C omega squared divided by K minus M omega squared. And then I factored the A out, and then minus M omega squared. But I want, because this is a fraction, I want to get a common denominator. So I'm going to have to multiply K by K minus M omega squared over K minus M omega squared. And I'm going to have to multiply the minus M omega squared by K minus M omega squared over K minus M omega squared. And now I'm going to get like fraction. So don't click off the video. See you reaching for the little exit button. Don't you dare. I'm going to get in the numerator, so common denominator in the bottom. In the numerator, I get K times K minus M omega squared. Let me write this term last. So I'm going to say minus M omega squared times K minus M omega squared, because I got to trick up my sleeve. And then plus, I got a more fraction bar because I'm not done. This was C omega quantity squared, so parentheses, C omega squared. Then this all times A equals F sub 0. These first two terms, notice the like parentheses. We got factoring by grouping. Factoring by grouping. A hidden gem. So if I factor this like term out of just the first two pieces, That's k minus m omega squared times the remaining stuff, which is k minus m omega squared as well. Sort of a bit of deja vu there. And then plus, don't forget about this, that's my c omega quantity squared, all divided by k minus m omega squared. This is all times a. This is equal to f sub 0. All right. And so this is stuff squared. So this is k minus m omega squared quantity squared plus we got c omega squared all divided by k minus m omega squared times a equals f sub 0. So naturally, what do we want to do? We want to solve for a. So multiply by the reciprocal. So then a is equal to f sub 0 times, and the numerator is k minus m omega squared divided by, multiplying by the reciprocal, so now this is in the bottom, k minus m omega squared quantity squared plus parentheses c omega squared. This is a. Now that I know a, I can find b. Let's find b. What was the relationship? My substitution said b was c omega over k minus m omega squared times a. So c omega over k minus m omega squared times a, but a is this thing, which is, let me write this stuff first, k minus m omega squared over k minus m omega squared squared plus c omega squared times f sub 0. And what does this give me for b? I want you to notice on top and bottom, k minus m omega squared cancels. So on top, I'm left with c omega divided by, on bottom, I'm left with that k minus m omega squared squared plus c omega squared, and then this is times f sub 0. And this is b. So I'll box it and make a note for myself. This is b, this stuff here. I got more room because we got more to do. I want to build that, so this gives me a and b for my cosine omega t and my sine omega t, which is great, but I want to make this into one sinusoidal function. So I really want to find c, which is the square root of a squared plus b squared. Don't get mad at me, because we're almost done. And then we can do some more problems. C is the square root of, I want to square a. Well, okay, so if I square this, I'm going to get f sub 0 squared, and then all of this stuff squared. So what is it going to look like? F sub 0 squared. And then I'm going to get, on top, I'm going to get, let me do the squaring separately. The top squared, the bottom squared, but don't break them up or anything like that. I'm trying to do this the nicest way. So top squared, k minus m omega squared, and that's going to now be squared because I'm squaring a, divided by the bottom squared, and that was k minus m omega squared squared plus c omega quantity squared, and that's all now being squared, plus, now I want b squared. What was b? Well, that's going to have another f sub 0 squared, and then we're going to have c omega being squared here, and then the bottom is the same, and I'm squaring it. So that should give me a common denominator at least, right? That's not so bad. Could be worse. That's k minus m omega squared quantity squared plus c omega quantity squared, and all of this is a quantity that is going to be squared. Yeah, that's what I got. These are like fractions. Thank goodness. So what I can do right away, I notice both terms have an f sub 0 squared in them, so I'm going to actually factor that right in front. And for the rest of the stuff, I can write that all as one fraction over the common denominator. The common denominator is k minus m omega squared squared plus c omega squared, but then that, in turn, is being squared. And the numerator is, what do you know, k minus m omega squared quantity squared plus, because I factored these f sub 0 squareds out, plus c omega squared. I want you to notice, here I got stuff to the power of 1. Here I got same stuff to the power of 2. So this is going to reduce. So let's see, what do we have for c? Well, first, if I split up the square root, I have the square root of f sub 0 squared, which is f sub 0, times, I have the square root of, and think of this sort of like, I'll give sort of a little bit of inspiration over here. Think of this kind of like square root of x over x squared. So if I just do the division, here I'm going to be left with 1 on top, divided by, and then it's going to be this stuff now to the power of 1. So now I have k minus m omega squared quantity squared plus c omega quantity squared, and it's no longer squared because I reduced. Now I can use the quotient property of the radical, say square root of 1 is 1, and then I got square root of the stuff in the bottom, so I can write this as c equals, square root of 1 is 1, I can write f sub 0 on top, so the numerator is not alone, it's got a friend, and then over square root of, parentheses, k minus m omega squared quantity squared plus c omega squared. And this is what that coefficient capital C will look like. I have a general form for it. I have a formula for it now. I wouldn't say to memorize this necessarily. If you do, great. If you don't, then you can always generate this. Again, you don't have to do what I did, but you could take a specific example. You could theoretically solve for A and B numerically. Then you could do the usual stuff like when we found capital C, because we've done this before, just never in an abstract sense. Like here, for example, I did it, here I did it. But now what I have is a formula for it. So if I want to take a look at, I don't know, maybe 2 examples of practical resonance, I can plug it into this formula. So that's the advantage, is that now, if I want to look at many examples, I don't always have to do it organically from the start. I can plug into this formula since I went through this pretty fun process of generating it. So it's worth something. And now I want to copy it here so I don't have to keep flipping too far up. C, what was that? F sub 0 divided by, I can't forget it because it's etched into my brain. Now it's k minus m omega squared plus c omega quantity squared. This guy, this coefficient, capital C for fun. Now I can use this for systems of this form to investigate the possibility of practical resonance of the system. We're going to talk a bit more about practical resonance in that behind the scenes video, so check that one out. But let's talk a bit about it now. Practical resonance is a maximum for this coefficient C of omega. What is this coefficient doing? This coefficient C of omega, it's a function, so call it capital C if you want. I'm calling it C of omega since it is a function of omega. It's sort of the variable there. It gives me amplitude. And that's important for these sinusoidal functions to know how far up and down they go. I want to know the amplitude of them. And I want to know where I have a maximum for that, because that's going to be the wildest behavior then of the system that I have. So practical resonance is a maximum for the amplitude as a function of omega at a frequency omega, where omega is some positive value, some positive frequency. So that's the idea here. We're looking for what frequency is going to give us a maximum for our amplitude when thinking about that forcing function. And now we get to take a look at the possibility of practical resonance of the system. So okay, so what was it? C is f sub 0 divided by square root of, we had k minus m omega squared plus c omega quantity squared. And now that I have the system given, I can generate the system. I could say 1 x double prime plus 2x prime plus 2x equals 2 cosine omega t. And I can find A, I can find B, I can find capital C, or, ready? You probably thought I had lost my mind earlier. Why is he doing this? Don't torture us. I did this so now I can find this function C and just plug in. F sub 0 is 2 divided by square root of k is 1. Oh, sorry, k is 2. K is 2 minus m is 1 times omega squared plus c is 2 omega quantity squared. So I can build this right away. I don't have to build A, I don't have to build B, since I went through all of this work. And this gives me a function, what is this? 2 divided by square root of, if I FOIL, 2 times 2 gives me 4. I get a minus 2 omega squared, another minus 2 omega squared gives me minus 4 omega squared. Negative omega squared times negative omega squared gives me positive omega to the 4th. And then plus, if I do 2 omega times 2 omega, gives me 4 omega squared. Just barely fits. And then now let's clean this up. So C is equal to 2 divided by square root of, I have omega to the 4th. Negative 4 omega squared plus 4 omega squared cancels, so I'm left with plus 4. And this is my function of omega. This is that amplitude in front. We say we build this into C times cosine omega t minus alpha. This is this coefficient in front that's giving me the amplitude for the system. I want to point out right away that my denominator is non-zero, right? W to the 4th plus 4 can never be 0, since it's either going to be something positive or 0 plus 4 is then always positive. So it's never 0, and it's never going to be negative, so nothing imaginary. But what I want to do is I want to find a maximum for C of omega. So we think, well, how can I find a maximum for a function? To do this, I want to set C prime of omega equal to 0, and where C prime of omega is undefined as well. This is also a critical point. It isn't just setting the derivative equal to 0, it's finding where it's undefined as well. And then from there, we solve for omega to try to find these. And remember, omega has to be some positive frequency. Well, okay, so here's my function. And for differentiation, just think of it as a function of omega, and I would say rewrite it. 2 times, here we can say omega to the 4th plus 4, all to the power of negative 1/2, since I got a square root in the denominator. So then C prime, in terms of omega, chain rule, I get 2 times negative 1/2 times stuff to the power of negative 3/2. My inner function, I write back inside omega to the 4th plus 4. Stylus. Come on. Don't do that. Don't do that. Times the inner derivative. And the inner derivative with respect to omega, well, derivative 4 is 0. Derivative of omega to the 4th gives me 4 omega cubed. Clean up the derivative, set it equal to 0. So 0 equals 2 times negative 1/2 is just negative 1. 4 omega cubed is going to stay in the numerator, divided by, I can bring this down and make it omega to the 4th plus 4 to the power of positive 3/2. Now we already said that the denominator is never going to be 0. The nom does not equal 0. So that's good. So nothing's going to be undefined here. So then the only possibility, and I set it equal to 0, so it's not going to be undefined, but it will be equal to 0 when the numerator is 0. So this is going to happen when negative 4 omega cubed is equal to 0, which means that omega cubed is equal to 0, which means that omega is 0. So what we're saying right now is that the only possibility of practical resonance of the system would happen at a frequency of 0. However, 0 is not a frequency. I wouldn't even call it a pseudo frequency because it's not trying to even give me anything, not even trying to behave like that. Not a frequency at all. So we solved for it, but this, and remember, we're not allowed. That omega has to be greater than 0. Some finite frequency that's positive. We can sort of explain why this isn't a possibility. So this, we're going to say, not gonna work. So we would start by saying there is no practical resonance to the system. But we can explain why this frequency doesn't make sense. And in general, so we said we want c times cosine of omega t minus alpha. We want to find some frequency which is going to generate a maximum amplitude, which then is something that we want to consider in our system, right? Because that could be potentially hazardous, right? If I have some wild, crazy amplitude that results from a specific frequency, I might want to stay away from that frequency, right? It seems kind of like it'd be a really great blockbuster thriller, right? Oh no, the frequency omega is here and it's going to give us this amplitude and it's maximum and it's too much and it's going to terrorize the city. But then, like, I don't know, you're the superhero with differential equations and you're like, I saw this coming from a mile away. I already solved the differential equation. I'm going to save the world. And it's like, yeah, you're here to save us. Nice. Basically. But if omega is equal to 0, that's not really a frequency because we get c times cosine of 0t minus alpha, which 0t is 0, so we get c times cosine of negative alpha, and you know, not that we have to mention, but cosine is an even function, so cosine of negative alpha is the same as cosine of positive alpha, but this is not sinusoidal. This is not a function. This is a number. This is a constant. There's no function of t anymore, so we just get a number times a number, which is a constant, which is not oscillating. So this is not oscillating. So we say, well, okay, so in that case, we were prepared to make this comment. There is no practical resonance in this system. The only feasible value we found was omega equals 0, and that's not suitable for what we're trying to do. So we say, nah, not going to happen. Let's take a look at one more example, then we're going to be done. But head on over to take a look at the behind the scenes lecture video for the section where we talk more about these systems in depth and we get sort of a better idea as to what's happening while not necessarily exploring so many examples. But so let's go ahead and let's use our formula again. So C is equal to, so same idea, but now I have a new setup. I'm not even going to write out the system since I have that nice closed form. F sub 0 is 50 divided by, and then we had square root of, parentheses, it was k minus m omega squared, so 45, minus m is 1 times omega squared, and that was being squared, plus c times omega, which is 6 times omega, and then that's being squared. So this is my amplitude function. I can build it right away. I don't have to go through the usual behavior, unless I want to. I can do that too. That's always an option. If you're just doing one problem, that would maybe be faster. If you're doing 2 problems, too close to tell. If you want to do like 7 problems, you want to build this function that I'm using. Pro tip. But now I want to find the derivative of it. Now, and you could expand this out. I think that's great. But just for the sake of getting through it a bit faster, let me just do the derivatives. Let me write c, my function of omega, as 50 times, and then here I have 45 minus m omega squared quantity squared plus, let me actually write this as, this is 36 omega squared since it's fast to square that, all to the power of negative 1/2. I can just find the derivative right away. Should you expand this out? Maybe that's preferable, but here we can just take the derivative. 50 comes along, chain rule, outer derivative is negative 1/2, and then stuff to the power of negative 3/2, and then this is inside 45 minus m omega squared squared plus 36 omega squared times the inner derivative, and I think I'm going to run out of room, so let me write the inner derivative underneath. So derivative of stuff squared is 2 times stuff to the power of 1 times the inner derivative of this with respect to omega. Derivative of 45 is 0. The derivative of minus m omega squared gives me minus 2m omega. And then plus, so this is my times my inner derivative, plus derivative of 36 omega squared is going to give me 36 times 2 is 72 omega. Now, if I was trying to clean this up, and again, we'll sort of talk about it in general, C prime 50 times negative 1/2 is negative 25. And then this stuff is going to be in the bottom, and that's my 45 minus I'm so sorry. Why do I have an M in here? It's just been one of those days. I don't even know what I'm doing. I mean, I know what I'm doing. I just don't know why there's an M there. You probably have been wondering that for a long time. And why didn't you say something? I'm right here. I'm looking at it like we plugged in M. Why do I keep writing it? This looks better, right? All I can do is say I'm sorry. This is what happens when you generate crazy coefficients and you get all excited with the stylus. I have no words. I'm just thinking that there's probably only 2 of you that have got to this point in the lecture video. I'm kind of kidding, but who knows. If you did make it this far, just go to the discussion board and say, the teacher made a mistake. And I'm going to comment back, I'm going to say, I did. But I fixed it in real time. And I don't really feel like redoing this lecture for that. This is a lot of work already. You're worth more, though, so I will mention that. If you want me to redo this lecture, let me know. I'll redo it. But I just want... M was there. I don't know why M was there. I'm still creeped out by that. It's like this problem is cursed. And then, so this negative 25, stuff to the negative 3/2 now, divided by stuff to the 3/2. Inner derivative is what we're here for. Let's get this one out of the way, and then we can talk more about this stuff. I still have an M. Where are all the M's coming from? Did you do that? We said that M was 1. I'm losing it. It's that part of the semester where you're just like, I'm spent. I want to continue on, but I don't know if it's safe. I'm just kidding. I'm having a good time here. I'm going to leave it to you to show that this denominator will not be negative and can't be 0. You can do that using, if you expand it out using the quadratic formula, it's only going to give you imaginary stuff. So we say no real frequency is going to cause C prime to be undefined. So we're going to turn our attention to, and I think it's already been a while, so we're going to try to wrap this up, turn our attention to the inner derivative could be 0. So 0 equals, we'll say C prime is not undefined for any real frequency, and that this could generate a 0, and that's going to be my, if I want to expand this out a bit, 2 times negative 2 gives me a negative 4 omega times 45 minus omega squared plus 72 omega. And let's see if we can rock and roll with this a bit. So 0 equals, if I sort of think about this as 2 times 45 is 90, times another 2 is a 180, it's a negative 180 omega. Minus negative is plus 4 omega cubed now, plus 72 omega. I don't see any more m's, and I'm happy about that. Oh my goodness. That's going to creep me out for the rest of the day. There are all these m's that came out of nowhere. I don't even know why they showed up. I'm not even sure that I wrote them, to be honest. I think I did, but it doesn't feel normal. Combine the like terms. Negative 180 omega plus 72 omega is negative 108 omega. And here we can factor. Bring an omega out. We got 4 omega squared minus 108. Now, we can say something right away. Omega could be 0. It's going to generate a true statement, but that's not a frequency, so that's not what we're looking for. So we're going to say omega shouldn't be 0. So I can divide by it or exclude that factor. So 0 then is equal to 4 omega squared minus 108. If I add 108 over, 108 equals 4 omega squared. If I divide both sides by 4, what is that, 27? equals omega squared, and then taking the square root. Remember, omega as a frequency should be not 0 and non-negative. So we're just looking at the principal square root. So omega would just be square root of 27. And then if I want to use the product property of the radical, I could say 27 is 9 times 3, where then the frequency, omega square root of 9 is 3 times square root of 3. And this would be, this works. So there is a possibility of practical resonance to the system. So there is a potential for practical resonance of the system at a frequency of omega equals 3 times square root of 3. Now, we'll talk a bit more about practical resonance colloquially in that behind the scenes video, but just as sort of a rough idea, we know that this is a frequency that will generate the largest possible amplitude, a maximum for the amplitude. So we at least want to be prepared for that, to know that if we're tuning our machinery, we perhaps maybe want to stay away from this frequency. And then in addition to that, if the frequency of our forcing function matches that frequency of the complementary solution, of the homogeneous solution, sort of the natural frequency of the system, we would say, then that carries a wild potential of resonance disaster. And let's talk about that more, but in another video. I gotta get out of here. I'm still creeped out by all those M's I had. Ugh. Looks better now. Well, let's pretend that never happened. I'd be happy about that. But hey, we're done with the section, and I think that's a good thing. I'm gonna put the homework in the homework jar. Please go over to our online homework utility, take a look at those problems. I have one extra page here for notes. You know what I'm gonna say. Look out for wild M's. Creepy. Don't like. Unsubscribe. But thank you so much for hanging out with me with this lecture video. I'm gonna see you for behind the scenes on this content and for more lecture material coming soon. Remember though, keep learning, keep dreaming, and always follow your heart. And watch out for those M's.